all the assignments? Yeah, good evening. How many assignments are done till now?
I completed the DLD assessment,
Okay,
assessment 1, and I go through the Verilog sessions now.
okay, fine.
Same here.
So, ma'am,
You need to go through Verilog sessions. Okay, Verilog assignments, any assignments did? And also I have shared the flip-flops codes. Have you gone through those flip-flop codes?
no, ma'am.
Okay, so when will you complete those? Or at least do you have any doubts in that? Any doubts in the flip-flop codes or any combinational logic codes? And also I have shared some problem statements. So any doubts in the problem statements, how to write the programming in Verilog?
Still no, ma'am. If you have any doubt, I you, ma'am.
Prasanti, one thing I want to ask.
Yeah, please tell.
So these assignments we need to submit through like through soft. So we need to submit some soft copy.
Not soft copy. On first day I told you, right, how to submit a Verilog system Verilog UVM assignments. Did you remember that? No? Okay, see here. So you will have the sheets, Google Sheets, right? So from here also
Yeah.
you can select the Google Sheet. So open a Google Sheet and here you can take like this first sheet one. You can take sheet one name as a Verilog assignment one.
Hmm.
Next to add another sheet, Verilog assignment 2. Next like that assignment 3, assignment 4, and then system Verilog assignment 1, assignment 2, UVM assignment 1, UVM assignment 2. I have shared the question and answers. Some QA, choose the correct answers. Choose the correct answers. I will share you the answers directly. Okay. But whatever the simulation problem statements I have given, you need to write down the problem statement here. Suppose in first line, first problem statement you can write. Okay. So any problem statement, suppose, and in the B column, whatever the output link is there, EDA playground link for this problem statement, you need to attach that link here, whatever the program you are writing.
Okay.
Did you understood like that?
Yes,
So
yes,
all
ma'am.
assignments you will be having in a one page. In future, if you
Hmm.
want to refer, that would be easy for you. And also I can check easily every assignment and I can correct your like any output is wrong. So I also can access easily.
Okay, got your point.
Yeah. Suppose here there is an example like this.
Hmm.
So already you have saved in your work area, right? Just copy this link here and you can paste that near your question. So you will be getting all play EDA playground link here and left side all questions. And you can save also in your EDA playground also you will find all Verilog assignment questions. Okay.
Okay.
Yeah. So any other doubts others? Okay, fine. So now today we will discuss into the registers. Okay, registers and delays in the circuits are there. Delays we will discuss in the next session. Once registers counters completed in a Verilog program, one day we will discuss on delays, concatenation delay and concatenation delay. propagation delay, and also setup time, hold time analysis, static timing analysis. All these things we will discuss in the one session. Okay. Meanwhile, everyone complete all the basic things, like you have pending works, right? So if everyone completed all the pending works, then we will discuss static timing analysis concepts. Okay, by end of the month. Okay. So registers. What is mean by a register? What is mean by a register?
It is set of flip-flop.
Set of flip-flop. Okay. How much size it will store? How much size of data will be stored in the register?
8-bit.
8-bit. Okay. For 8-bit storage, how many number of flip-flops are required?
8.
Will it store only 8-bit? Can't we store word size, double word?
8 to 64 bits, ma'am.
8 to 64. Okay. What are the different types of registers are there in digital electronics or overall in processors like that?
8-bit register,
Okay.
8, 8, 16, 32.
Okay. Can't we
Multiple in, multiple out.
Okay.
That is basically shift register.
Okay. Yeah, fine. Any other answers, others? Okay. So in a register is nothing but, suppose flip-flop means it's a single bit storage element. Okay. So for which flip-flop we use to store the data? Mostly D flip-flop. D flip-flop will store the data, memory state. Okay. So whenever we are connecting multiple number of D flip-flops in a cascade manner, it will work like a register. Okay. However, ripple carry adder or multi bit adder or subtractor we are using, n bit adder and bit subtractor, where we are connecting full arrows in a ripple, like propagating one carry to another carry. We are connecting like that. That's what we call as a ripple carry adder. Okay. In the same way, to store multiple number of bits, we use the cascade connection of flip-flops. That's what we call as a registers. Okay. So if you want to store 8-bit data, 8 number of flip-flops are required. If you want to store 32-bit data, 64-bit data, 128-bit data, 256-bit data, whatever the size, we can connect any size. Okay, by using those many number of flip-flops. Nowadays, everything we are working with the 126, 251. 164 and 256 type of data only, right? Not 32, just 32-bit or 8-bit storage. Okay. So register is nothing but where we connect a multiple number of flip-flops. Okay, and we store n-bit data parallelly. So what is the purpose of register means? That's what, to store the data. How many types of registers are there? Actually, in electronics, in digital electronics, we have only shift registers. Okay. But commonly we have lot of registers. If you go with a microprocessor language or microcontroller language, there we use some architecture. If you remember, we connect one bus and control signals will be there, and there will be a like ALU connections, ALU, arithmetic logical unit block will be there, and special purpose registers, general purpose registers will be there. So those types of registers will be different: special purpose register, general purpose register. So there will be a bus connection like this. To this bus connection, ALU will be there, and to the ALU some blocks, counters, or some multipliers will be connected here. Special purpose register, like a program counter, is a special purpose register, and there will be a accumulator. Accumulator is also a special purpose register, and there will be general purpose register, R1, R2, R3, R4. There are some general purpose register which we use in a microprocessor language. Okay, so special purpose register means specially for specific condition we use the special purpose register, not just commonly use it to store the data, but it do some specific operation. Like accumulator is there. Accumulator is a register within a CPU, central processing unit. It is used to store the immediate result of complex calculations, mainly to hold the data of complex calculations. That's what accumulator. Okay, it do the multi-step calculation and it store the result. Like the program counter is there. Program counter is also a special purpose register where we get the multiple data from the memory. Suppose here memory is there, RISC-V processor is there. RISC-V processor will get the data. Okay, program counter in a fetch stage, it will fetch the data from the memory block. So how it is fetching the data? Through byte addressing or through bit addressing, it will fetch the data and send to the next decode state. Okay, like the program counter is used to fetch the data from the memory. That is one specific operation. Okay, like the general purpose register R1, R2, R3, R4. So if you see, whenever we are writing some microprocessor language instruction set, add R1 comma R2 comma R3, that means source register comma destination register comma source registers. Like that subtraction, sub R1 comma R2 comma R3. So source register, for source registers we are doing the subtraction and storing the data in a destination register. Like that, based on the instruction set, we have different instruction set, right? Immediate instruction or register instruction set, or jump type instructions or branch type instructions. Based on that, we have the multiple number of instruction set and we do the operation. Just a second. Okay, we use those type of registers here, like a general purpose register and special purpose register. But for digital electronics, whatever we are learning in our curriculum, we don't have those type of registers and all. Okay, we just have a shift registers. Okay, shift right, shift left, parallel input, parallel output data, bidirectional shift register, and a universal shift register. These are the different combinations we have. We will discuss one by one. Okay, did you all understood what are the different types of registers we have? Hello. Yeah, am I audible?
Yes, ma'am.
Any doubt still here?
No, ma'am.
No.
Okay. So which flip-flop is used in the register? I already told you, right? Mostly we use a D flip-flop for storage element. And how does a register work? So how does a register work in the sense, whatever the registers we have, we will discuss that functionality. Okay, remaining I told, right? What are the general purpose register and special purpose register? If you see here, program counter, which is used to fetch the data, address register to store the address data, processor, it's a processor which stores 16-bit data, and a memory. Instruction register in the sense it decodes some instructions only for particular storing purpose, instruction storing purpose. We use the instruction register. Like the temporary register to store some temporary data while we are performing some task, while we are working on some instruction. For that purpose we use temporary register. Next, data register to store the output data. We use the input data or output data, whatever. We use the data register. And like input register, output register, accumulator, these all are special purpose register where we use normally in a CPU programming language. Okay. But in digital electronics, we have a shift registers like serial in, serial out, serial in, parallel out, parallel in, serial out, parallel in, parallel out, bidirectional shift register, universal shift register. Okay. So mostly we will discuss in theory wise and then we will write the program for all this. Okay, I will tell you each one in each style. Suppose serial in, serial out, we will discuss in a structural modeling. Serial in, parallel out, we'll discuss in a behavioral modeling. Next one we'll discuss in some like a continuous assignment or some other models in a easy way, and I will tell you all the models, each one, then you can do practice. Okay, next, bidirectional universal. So first one is a serial input, serial output, shift register. Okay, so here input is applying D input. Okay, suppose I am considering input as a 4-bit size, 1011. Okay, so first this one is shifted here in the first clock cycle, and then this one will be getting output here, and this one will be getting here, and this one will be output here, and this one will be getting here. And next bit, what is the next bit? Next, this one. So whenever this one is getting here, then this one will get here, and this one will get here, then this one will get here, and when this one here getting here, this one will be getting here. Okay, and then now this 0. Okay, so 0, whenever this one is getting to second flip flop, here we will get a 0. Okay, so whenever this one is getting to here, this 0 will be getting here. Like that, whenever this one will get here, this 0 will get here, and first one will get at the output side. Okay, and last one, this one. This one will be shifted to here, here to here, here to here, and here to here. Okay, so finally, how many clock cycles will be required to get all these 4 outputs at here? 1, 0, 1, 1. In first clock cycle, this one is shifting, and then when it shift to here, next one will shifted here. Whenever it shift to here, this one will be shifted here, and 0 will be shifting here. And whenever it shift here, this one will be shifted here, this 0 will be shifted here, and finally this one will be getting here. Okay, so whenever we get the output here, this one will be shifted here, 0 will be shifted here, and this one will be shifted here. So next, this one also will get, and next then 0 will be shifted here, 1 will be shifted, 0 also will get, and then 1 will be shifted here, then we will get 1 here. So output will be 1, 0, 1, 1. So how do we get, in how many number of clock cycles we will get the output as a 1, 0, 1, 1? Hello. Fast.
Hello.
Four o'clock cycle?
Only 4 clock cycles, both for input and output. Huh?
Sorry, 8.
8. Okay, how it is 8?
In first clock, one will be shifted to flip flop 2.
Okay.
And second clock 0 will be shifted to flip flop 3 to flip flop 2.
Okay.
And one move forward to flip flop 1.
Okay. Suppose if I am considering same as a parallel in parallel outer. Okay, so input all getting parallelly like this, and output is getting parallelly here. Parallel 4-bit shift register. So how many clock cycles will be required at the input side and output side?
Then
Hmm?
4 cycles.
4 cycles. How?
Because doing an operation within the 1 cycles, output in parallel. So
Hmm.
and also flip flops are 4.
Hmm. What about input then? Others, tell some answers. Vinita, Lahari, Rakshita, Sai. Suppose I am transferring 32-bit data parallelly like this. Okay, 32-bit data I'm sending in a parallelly, and same 32-bit data I'm transferring serially like this, each bit serially. So here how many clock cycles are required to send the 32-bit data parallelly, and how many number of clock cycles required to send the 32-bit data parallelly?
For parallelly 1 cycle, for serially each cycle, each bit like 32 cycles.
Okay, then how many clock cycles will be required here in parallel out for 4-bit?
Parallel in and parallel. So 5 cycles.
5? How? Just now you said 1 cycle for all bit, right? Yeah.
Yeah. For parallel in, it is 1 cycle. For
Hmm.
input, for output is it's a parallel. Then only one more cycle, right? Then 2 cycles.
Okay, 2 cycles. Huh?
Yeah. If it is parallel, yeah. Parallel output.
Okay. What about others? Any answers from your side? Rakshita?
No, ma'am.
Can you tell me here, Rakshita, how many clock cycles required in parallel transmission for 32-bit, and here in serial transmission, how many cycles are required?
Ma'am, I think.
Hmm?
Ma'am, 1 clock cycle only need, no, ma'am. For
Okay.
single clock signal simultaneous.
For serial?
For serial, I think 4, ma'am.
4.
Yeah, ma'am.
For this shift register you are telling.
Yes, ma'am.
Okay. Okay, see here. In parallel communication, whatever the number of data you are considering, whatever the size of the data, all the bits will be transmitted in a parallelly. That means for all the bits, we will use only one common clock. Okay, by using one single clock cycle, within a single clock cycle, all the data will send parallelly. Okay, but in serial communication, it's not like that. Every bit will be transmitted for each cycle. So first cycle 0 bit, second cycle 1, third cycle 1, fourth cycle 1. Like that, 8 bit means 8 clock cycles, 32 bit means 32 clock cycles, 4 bit means 4 clock cycles. Okay, so here for parallel input, parallel output, all the data is transmitting parallelly. That means all the data will get at a time in a single clock cycle. Okay, so for input transmission 1 clock cycle, and output is getting in a parallel way. So all outputs will get at a same time, single clock cycle only all the outputs will get. Okay, so for input side 1 clock cycle, output side 1 clock cycle. Within a 2 clock cycles we will get the output in parallel input, parallel output. Okay, but for serial input, serial output, for serial in, serial out,
Number of bits in input plus number of bits in output total.
so for serial in, serial out, suppose I am taking as a 4-bit input. So to transmit input side, 4-bit serial shift. So 4 clock cycles will be getting, and to transfer at the output side, to get at the output side will require 4 clock cycles. Okay. Totally at 7th clock cycle, we will get the output if we don't consider first clock cycle. Okay. So like that, we will need to calculate for serial in, serial out, parallel in, parallel out, parallel in, serial out. So how it will be working? Parallel in, the serial out, or else serial in, parallel out, suppose here. So how many number of clock cycles will be required at the input side and output side? Suppose serial input 0 1 1 0 I am applying. Okay, and output is parallel. At what clock cycle we will get the output as 0 1 1 0. At what clock cycle? You need not to take this much of time.
Fifth cycle.
Fifth cycle. Okay, so for shifting all the bits, first 0 bit will be shifted here. In the second clock cycle, 0 bit will be shifted to here, and this one will be shifted here. In third clock cycle, this 0 will be shifted here, and that one will be shifted here, and another one will be shifted here. In fourth clock cycle, this 0 will be shifted here, and this one will be shifted here, and this one will be shifted here, and this 0 will be shifted here. So for shifting all the data till here, 4 clock cycles are required. So after this, output is parallel. So now here we'll get 0 as output, and here 1 as output, and here 1 as output, and here 0 as output. All the data will get output in a single clock cycle. Once we get all the output here at a time, the clock will be triggered to the output. So once we get all the data in each flip-flop, then output will be getting parallelly here. 5 clock cycles. Clear, everyone?
Yeah, ma'am.
Yes.
Yes, ma'am.
Okay. Next, parallel in, serial out also same. Input is given parallelly, but here what is the difference means for parallel input, serial output, before all the diagrams are normal, just block diagrams. Okay, but here simple just we use extra signal called shift or load. Okay, shift or load means what? If you observe here, shift load bar or shift bar load. Okay, so if shift is high, load will be 0. If load is high, shift will be 0. That means load and shift will not done by at a time. This is a parallel input, serial output. Parallel input to serial output. That means first you are loading the data parallelly. Once all the data is loaded parallelly, so you suppose I will show you, wait, the functionality, so that you will, when you are writing the program, it will be easy. Okay, suppose these are the parallel inputs B0, B1, B2, B3. I am doing here 0 1 1 0. 0 1 1 0 is the parallel input. I want to send this parallel input to here, loading the data. Loading the data means what? That 0 should be getting here, this 1 should get here to this input, and this 1 will be getting here to this input, and 0 will be getting here to to the D3 input. That's what we tell load. Okay. Once load is done, then we can shift. Then only we get the output at the last after shifting. Okay. So suppose shift by load bar is equal to 0. Suppose. Okay. That means shift is high, load bar. Load bar is a active low signal. When will be active low signal will be activated? Whenever 0 as a input. So I'm taking load bar as a 0. Okay. So now load is high. Load is high means this data will be loaded to here. Okay. So check the functionality here. This 0 B0. Okay, B0 is getting 0. This one is directly loading. Okay. And this one, first this one will be giving here. And whatever the load bar data is there here, 0 will get here. And this signal here, this 1 will get here. And this signal, this 0 will get here. Okay. End operation. End operation 0 into 1. 0, 0 into 1, 0. 0 plus 0, 0. Okay, then it's wrong. Wait. Then we need to consider as a shift bar load. Shift bar load. Okay, is equal to 1. Shift bar equal to load equal to 1. Then this not value will be 0 or 1. And this will be the 1. So 1 plus 1, 1. And here 0. And this will be 0. Here 0. 0 plus 1. Output is 1. Okay, load is high. And here this is a 1. And here this signal is also 1. And this signal will be 0. And here whatever the signal here, it's 1. So 0 into 0, 0, 1 into 1, 1. So 0 plus 1, 1 here. Okay. And here B3. So here this one B3 and this one 1. And this one also 1. And this is 0. 0 into 1, 0. 0 into 1, 0. Output is 0. So this is what the internal operation for loading the data. Okay. Now you need to make this as a 0. That means shift is high. Okay. So whenever you make this 0, now shift will be high. So same data will be getting at the output and it will be shifted to here. Parallel in a serial out. So finally we will get the output here at 4 clock cycles. Did you understood? While you are writing the program, how do we write the program? You can write in the structural modeling, but it will be a bit confusing. But if you write in a behavioral modeling, suppose I am writing always at the rate of posage clock shift. Initially shift is high. Then how you need to shift the data? Like A right shift B, like D0 right shift of D1. Okay. Load, when load is high, 2 signals you need to take. Whenever load is high, B0, B1, B2, B3 should get D0, D1, D2, D3. Okay. So D is equal to B when load is high. So simple program we need to write in a behavioral modeling. You already know, right? Behavioral modeling means it's like a simple language, like however we write the C programming in a simple functionality, we can write in a loops like that. Clear, everyone? So how many clock cycles will be required to get the output data here in parallel input, serial output? How many clock cycles are required?
8.
8. No. How 8? Why you are confusing? And where you are confusing? Parallel input means how much, how many number of clock cycles? All are parallel inputs only here, right? All these.
For input, clock cycle, ma'am. For output, 4 clock cycles.
For input, 1 clock cycle. Within a 1 clock cycle, we will load the data, all the data parallelly. But for output, shifting the data. So to shift here to here, 1 clock cycle, here to here, here to here, like that, here to here, 4 clock cycles will be required. So total 5 clock cycles. Okay. Clear,
Yes,
everyone?
ma'am.
Okay, ma'am.
Same.
Yes.
If that's what here we written more theory part, so you can go through the theory part, but it's whatever I discussed, that's okay. Okay, no need to go through deep into the theory. Okay, functionality wise, whatever we understood, that's clear. And coming to the bidirectional shift register. Okay, bidirectional shift register, universal shift register, we will discuss in the next session. As of now, we'll write the programming for these 4 registers. Okay. Okay then. So first one, serial input, serial output. Okay. So serial in, serial out. First, we will see in a structural modeling. Okay. Structural modeling means what? Serial in, serial out. First, we need to design one D flip-flop. Okay, this is the D flip-flop module we need to design. By using the D flip-flop module, we need to take a 4 copies. So by taking 4 copies, we need to connect internally. Okay, that's what serial in, serial out. So you will get exact diagram like this. Okay, if you write in a structural modeling. But if you write in a behavioral modeling, you won't get this structure. Okay, you just get some logical diagram. That's it. So if you see here, module, serial in, serial out, design program. So module, serial in, serial out register, D input is a input, and clock, clear, D out. Single input, single out. I mean single bit. Okay. So input D in, clock, clear, output D out. Next wire, internal wire connections, that is for main serial in, serial out. But before that, we need to design a D flip-flop, right? So from 14th line, if you observe, module, D flip-flop, input D, clock, clear, output Q. So how we write the program for D flip-flop? If clear is high, output should go to clear state, reset state 0. Or else, whatever D input is there, that input will get to the Q. That's why we are calling D as a storage purpose. Okay. If input is 1, output is also 1. If input is 0, output is also 0. For D flip-flop, right? So by using this module, DFF, we are taking 4 copies. Okay. So if you see from 7th line to 10th line, DFF 1, 8th line, second copy, 9th line, third copy, 10th one, 4th copy. So D1, D2, D3, D4 we are mentioning. Okay. So after taking copies, we need to make the connections. So whatever the connections are there here, 1 to 1, we need to make those connections. Okay. So how we are making those connections? Just we need to mention here for first flip-flop, what is the input? Clock clear, common for all flip-flops. Then what is the output? Q1 is the output. Second flip-flop, Q1 is the input, because whatever the output is getting here, that output will be input to the next flip-flop, right? So that's why Q1 is the input, clock clear common, Q2 is the output. Next Q2 is the output, clock clear common, Q3 is the output. I mean Q2 is the input here. Q3 is the input here, clock clear common, D out is the output. Serial in, a serial out, shift register using structural modeling. Okay. So if you want to write in a simple way like behavioral modeling, this is one another model. Okay, serial in, serial out, shift register in behavioral modeling. So if you see here in 8th line, always at the rate of POSH clock begin W of 3. W of 3 is a wire connection. Okay, because these internal all are wire connections, right? This is one wire connection, second wire connection, third wire connection, fourth wire connection. Fourth is the main output. Remaining these three all are wire connections. So that's why we have written here as a wire connection. So first W of 3. So for this O3, here Q3 is there, like Q1, Q2, Q3, Q4. Okay, first input we getting here as a DN. Next one here getting as a this same. Whatever the Q3 is there, same here we'll get. Okay, you can write any names Q3 or Q1, however you are starting that you are wish. But while connecting, carefully you need to check. Okay, because MSB and LSB bit, before also I have told you what happens if you take different MSB and LSB. Suppose while I am taking in a shift register, I am taking as a Q3, Q2, Q1, Q0. Okay. So at a declaration time, how you need to declare Q3 down to 0. 3 down to 0 Q. So this will be like this. 3 will be MSB, 0 will be LSB. You need to follow same format for all. Even test bench or design, whatever, need to follow same. Okay. But some of you will write, some students will write in the design, they will declare as a 3 down to 0. But in test bench, they will write as a 0 up to 3 Q. Okay. So whenever you write like this 0 up to 3Q, now Q will be starting with a Q0 and Q1 will be started here, Q2 will be started here, Q3 will be started here. So whatever the, suppose we are applying 0, 1, 1, 0. So here we will get as a, suppose 0, 1, 1, 1. So here we will get as a 1, 1, 1, 0. Okay. So most of these times output will be mismatched. Internal connections will be mismatched most of the cases. That's why for clear understanding, I will tell you whenever you are declaring for design, suppose up to down or down to up, try to design the same way for test bench also. Okay, in that case, we will avoid lot of confusions. Okay, because suppose when you take 3 down to 0, you are applying 0, 1, 0, 0. Here when you are taking here 0, 1, 0. Okay, you will think like both are same. I am applying 0, 1 for input, and here also I am applying 0, 1. But why output is not getting? You will think like that. But whatever you are applying here 0 up to 3, that is reversed. Here reversing the same input, it's going to reverse here. You took right only, but it will reverse the case. Okay, that's why to avoid those type of mistake, I no need to tell, Whenever you will practice, you will get understand while you are debugging, then only you will understand how to clear that issue. But I'm just explaining, okay, so to avoid those type of common issues. Okay, so that's why D is applying here W of 3, or you can use W of 0 also. And this same W of 3 applying to W of 2, second input. And this same second input is applying to third input, and this same third input applying to last one, W of 0. Okay. So this W of 0, serial in, serial out, right? So this wire connection output is assigning to the main output. Q is the main output. W is the wire connection. So this wire data is applying to the main output. Okay. So this is one style in simple way, and this one is a structural way. We do the synthesis, then you will understand the difference between both. Okay. Clear everyone till here?
Yes.
Okay. So I'm taking same example and open Quartus Prime. Did anyone facing any problem from Quartus Prime or model simulator? Are they working for you? Any issues with like videos accessing the sessions? Any issues you are facing?
No, ma'am.
Okay.
No.
So Verilog 1, I'm just replacing this name with the Verilog 1.3. And also we need not to use start with the numerical value. Okay. We always need to write with the alphabetical value only. Module name. You don't write all for Verilog 1. Create according to your design name and try to save all the designs. Okay. So compilation is done. Compilation means syntax errors, no syntax errors. Okay. So once compilation is done, it will go to the main tester. So it will check for the functionality. Okay. So if any functionality is wrong, we'll get understand that in simulation, not in synthesis. In synthesis, we'll check only for this syntax errors, compilation error. Because in synthesis, whatever we write, its task is to generate the netlist only, not to check internal functionality. Okay, that's why. See here, serial input, parallel output, shift register. Okay, so 4 boxes internally, whatever the program you have written, like this flip flop, D flip flop, multiplexer, input output. So every circuit internally you will get like this, because you have took the copies of D flip flops into four copies, right? So this is how we write the program for structural modeling: serial input, serial output, shift register. Clear everyone till here?
Yes.
Girls? So after doing synthesis, we need to do the simulation. Simulation in the sense applying the test vectors. Okay. So how we need to apply clear? We need to apply for clear signal. D input is the input, main input. Clock is also main input. So for these three, we need to generate the input and we'll check the output. Internal connections, wire connections, we don't need to take care. We don't need to bother about the internal connections. Okay. So how to write the test bench? So left side one is a test bench here. Module test bench, register input and outputs are declared here. Can you tell me why inputs must be declared as a reg data type and outputs are declared as a wire data type here? Hmm? Why inputs must be declared as a register and outputs must be declared as a wire?
Don't know, ma'am.
Don't know. Have you not gone through the Verilog session? Procedural assignment and continuous assignment?
No, ma'am.
Okay. So first complete those sessions because those are very important. Once you
O-
know those, then only you will try to answer these. Okay.
Okay, ma'am. Tomorrow I will complete it, ma'am.
Okay. Lahari, can you answer? Why do we take inputs
Yes,
as
ma'am.
registered? Yeah.
For procedural assignment, we need to declare output as register, and for continuous, we need to declare output as wire.
No. You need to tell in a proper way. Whatever you understand, okay, but you need to answer in a proper way. You need not to use output input
Okay.
like that.
Ma'am, because input stores a value, so that's why it choose a register.
Uh, Input will store the value. Huh?
Input declares the value.
Okay. So did you go through the procedural and continuous assignment statements?
No, ma'am. Just I am middle of the session, middle of
Okay.
the previous.
Okay. First go through that and then you can answer. Okay.
Yeah, okay.
Yeah, Lahari, tell me.
Yeah,
Whatever you're
ma'am.
thinking, that's correct.
Yeah.
Hmm. Yeah, tell me.
Procedural means we will use always, and always block we will use. So if we declare it as wire, it will throw an error, ma'am. So we need to declare it as reg type for the output. I mean RHS.
Okay. Vinita, can you answer? Okay, see, we have a two procedural assignment statements. One is a initial, one is a always. These two are procedural assignment statement. Whenever we use initial block, LHS side variables, we need not to tell as a output. LHS side variables must be declared with a reg data type only. Okay, RHS side variables can be declared as either reg data type or wire data type. Okay, so whenever we use always block, always is also a procedural assignment statement. So here also whenever LHS side variables should be declared with reg data type, RHS side variables can be declared with either reg or wire data type. Okay. Procedural assignment statements. But for continuous assignment statements, what are the continuous assignment statements? Lahari,
Ma'am, is it blocking or non-blocking? I mean,
no. Why you are forgetting the basics? What is the difference between begin end and fork join?
Yeah, ma'am, got it. Yes, yes. Sequential and parallel, right?
Hmm.
Yeah.
Then where we
So
use
for
the blocking and
continuous,
non-blocking?
yeah, ma'am, just got confused. Yeah.
Okay. Then what are the
For
continuous?
continuous,
Hmm.
for continuous assignment, sequential is initial begin end. For parallel it is initial fork join. And for the assignment, what we need to do is for continuous assignment, LHS will be wire data type, RHS will be reg.
Hmm. What is that continuous assignment means? Which keyword? Keyword we use, like initial, always. Which keyword we use?
Initial, ma'am.
No. Initial is already procedural assignment. Then how we tell it as a continuous? Maybe you forgot. Assign is a continuous assignment statement. Okay. Assign.
Yeah.
LHS side variable must be declared as a wire data type. RHS side variables must be declared as a reg data type. Don't
Reg
confuse
data type.
anyone. Okay, so these three everyone must know. Whatever you told the blocking and non-blocking assignment, within the initial block, if there are multiple number of statements, we use a begin end block. Statement 1, statement 2, statement 3. Then we use as a begin end block within the initial and within the always. Okay. So
Got it, ma'am.
fork join begin end means a sequential execution statement. Fork join means
Parallel
parallel
execution.
execution statement. Okay. So whatever the assignments, whatever the statements we are writing within the begin end, these execution may be blocking assignment. We didn't discuss about the blocking assignment, non-blocking assignment till now. We will discuss in the coming sessions after counters. Okay. So non-blocking assignment. So you need to follow, you need to understand, make a screenshot of this, like at least you can put it as a table. Okay, so where we get the fork join, where we get the begin end, where we get the blocking assignment, non-blocking assignment, like that you can make as a screenshot. Okay, so here we use the initial block. So LHS side variables must be declared with a reg data type. RHS side variables must be declared with a var data type. Suppose A is equal to B plus C. Okay. Now A is a LHS side variable. B is B, comma C is a RHS side variable. Okay. Now A must be declared as a reg data type. B and C can be declared as a reg or var data type. Okay. That's why here if you observe 14th, 19th line, how we are applying the input signals, input test vectors. D in equal to 0, clear equal to 1, clear equal to 0, D in equal to 1. In test bench, always we apply the inputs to uh, test vectors to inputs only, not outputs, right? Outputs we will get from the DUT. In the test bench, we apply the inputs to the input signals, test vectors to the input signals. Okay, so these input signals always left hand side to the initial block. Okay, that means initial is a procedural assignment statement. As these are left hand side, We always need to declare inputs as a reg data type and output as a wire data type. Okay, is it clear now, everyone? These are the must known rules in Verilog. Very simple rules only.
Okay, ma'am.
Okay, next. So here that is why we declare inputs as a reg. That is a blind, you need to remember, blind thing. Just inputs anywhere, in any case, we declare inputs as a reg data type, output as a wire data type, because we write in the procedural assignment statement in the test bench. Okay. To avoid this confusion, actually it's a lot of confusion, because there will be lot of inputs and lot of outputs. Every time you need to check reg or while, lot of confusion. So to avoid this, in system verilog we have a logic data type. By using a logic data type, you can declare whether it is a input or output. No need to check. For all variables we declare as a logic. Logic replace reg and wire. Okay, but here we don't use logic because it's a Verilog programming, right? In system Verilog, we don't have that limitation. Okay, next thing, eighth line. Eighth line is a DUT. That means interfacing our test bench with the design. Okay, what is the design name here? CISO, SISO Reg is the design name. So that design name you need to mention here, and DUT is just a CISO Reg name here. However, right side 7 to 10, if you observe here, DFF D1, DFF D2, DFF D3, D4. D1, D2, D3, D4 are just our names. For our clarity, we kept those names. Okay. Like that, here DUT is also just we can put any name. In place of DUT, I just put as a sys. I can put. But this line we call as a DUT, design under test. Okay. So we need to apply the port list here. D in, comma, clock, comma, clear, comma, D out. Then I already told you, right, how to generate the clock in Verilog HDL. We already generated a clock. So initially clock equal to 0, always at the rate of #5. For every 5 time unit, clock equal to 0101 not clock, like that. Next, initial begin. By using $monitor, we write the statement, printf statement. Then initially D in equal to 0, clear equal to 1, and then clear equal to 0, D in equal to 1. Next, initial begin $dump file dump vares. That means to open the waveform, we need to write the $dump file within the dump.vcd. In place of dump.vcd, you can also write a design name, CISO Reg. CISO Reg.vcd also you can write, or else dump.vcd also you can write. Okay. Dump vares. Dump vares means what? Dump file means this is a design file we are dumping into the test bench. That's what we call dump file. Yeah.
What is VCD derivation?
VCD means vector common destination. Something is there. I also forgot. VCD vector. Changing the dump. Vector change dump. Value change dump. Yeah. Dump.vcd means a value change dump. Okay, that means in dump file, every value, every change of value we are dumping here. Value change dump or vector change dump. We can say, wait. Value change dump only. Okay. Next here, $dump file, dump var means we will dump all the variables, whatever D input, clock, clear, DUT, all these signals we can dump into the dump variable, or else here also we can select you only which variables you need to dump and which are not required. We can select based on 0, 1. That thing we will discuss clearly in the test bench concept. Verification concepts are separate. We will discuss in that. Okay. So we'll do the simulation. I'm just opening the waveform here by default. So click on run. So after opening waveform, you will get the signals here. All signals you can dump. Okay, I will explain the waveform. So initially D input is a 0, D out is not getting C here. And Q1, Q2, Q3 clock from 0 to 1 like this. Clear initially 1, then after 5 time units clear is 0, right? You can check in the program. So initially at 0 simulation time clear equal to 0, 5 simulation time clear equal to clear equal to 1 initially, 5 simulation time clear equal to 0. Initially D equal to 0. Okay, so initially D equal to 0. So up to clear time the output will be in a 0 state only, because if we don't get the output up to clear state. Okay, so better I can put this signal down, then you will understand. Okay, see here. Clear is 0 initially. So till here. Once clear is high initially, so output will be 0. Once clear is 0, we'll get the output. Okay. So initially D0 is 0. So when do we get this output here in the next clock cycle after clear is 0? After getting here Q1, then in the next clock cycle we get at Q2 and then Q3 and then main output. Okay, so first clock cycle 1, clock cycle 2, clock cycle 3, clock cycle 4. Okay, for one single bit it took 4 clock cycles. Like that 4 bit means extra 3 clock cycles. Total 8 clock cycles it will be taking. Okay, and again next D1 0 1. So from here input is 1, then output 1 we got here in the next clock cycle, and here we got 1, and here we got 1, and here we got 1. So 4 clock cycles for this one, serially shifting. Okay, clear everyone?
Yeah, ma'am.
That is what we can call as a serial in, a serial out. Suppose here, okay, one input, I have considered D in as a one input. So it took 4 number of clock cycles. Okay. So D in as a 4 bit. Then what you need to take D in take as a test vector 3 down to 0. DIN, and output is also 4-bit. Okay. In the program, you need to change DIN, Dout. So DIN of 0 for first one. And then no need to take, in that case, no need to take Q1, Q2, Q3, Q4. You can take a D input to here, Q1, and D in 1 to here, D in 2 to here, D in 3 to here. So 4-bit, 8 clock cycles. Try with that and show the output like this. Okay. Will you do that? Hello.
Yes, yes, Prasanth.
Next, this one simple program in behavioral modeling. We'll check for this also. D input block Q. Getting. See here how it is getting shifting the values. See here Q, Q3, Q3, Q2, Q1, Q0. D is a input, D1 in this clock cycle. It is changing for negative edge of the clock. Okay, here it is positive edge of the clock. And here also positive edge of the clock. And here also positive edge. Okay, so input 1 here. This one is reflected to here, and this one is changing to here. This one to here, and this one to here. So see, shift how it is shifting. And here also internal signals how it is shifting. You need to understand every line to line. Okay. Clear everyone till here? Like that you can write in a different ways, behavioral modeling, data flow modeling, by using the excitation table, truth table. You will get the output expressions for register counters also. But those are complex. These are simple way. So however we written here, these all are simple way. Clear everyone? Shall we go to next example?
Prasanti,
Yeah.
in behavior model, okay, this reg is initialized with the zero.
Yeah, in synthesis it won't reflect, but
Yeah,
in
okay.
simulation wise we can. I will do the synthesis for this.
Okay.
But you won't get for behavioral modeling, you won't get the structured way. Before we got the structured simulation synthesis result, right? Like that we don't get, just give some multiplexer or small block. That's it.
And one more, just a small doubt. The structure model and the test bench we did, that is also for the CISO, right? Serial in, serial out.
Yes.
And the behavioral model also we have done for the CISO only, right?
Yes.
But the waveforms is bit different, right?
Where waveform both are same. See here how it is serially shifting from Q3. So initially Q3 and then Q2 and then Q1 and then Q0 here shifting one by one. And here also same. Here Q1, Q2, Q3, Q4. But here we have taken as a 3 down to 0. And here we have to 1, 2, 3, 1 up to 3.
1, 2, 3. Okay.
Q1, Q2, Q3, D out is a Q4. 1, 2,
Okay, maybe in the test bench it is different. That's why it is
both are
it is
different.
looking like okay.
Mm.
That's why it is looking like okay.
See here, for synthesis, compilation is free. Whatever you asked here, fourth line, this will reflect to test bench only, not synthesis. So actually we don't write. It's not a good practice to mention inputs in the design. Okay, but some cases we can consider RTL waiver. See how it is getting. It just will give like this simple block only, not in a structured way. Whatever we designed before. For any behavioral programming, it will give same way except finite state missions. Okay. And next, serial input, parallel output. Serial in parallel out also same structural modeling only, but serial in parallel out serial in parallel out. So here D flip flop, one D flip flop is took here, and this parallel output is there, right? We are taking as a temporary value, and after getting to the temporary value at a time we are getting the parallel output here. Okay, so for that how we are writing the program, see here, created one D flip flop and took 4 copies of D flip flop, connected, and whatever this Q1, Q2, Q3, Q4 are the temporary outputs. Okay, so if you see here, Q1, Q2, Q3, Q4, we are storing the data, getting the data output to the temporary variables, and then assigning main output D of 0. Q1 value is assigning to D of 0, D of 1. Q2 is assigning to D of 1. Q3 is assigning to D of 2. Q4 is assigning to D of 3, like that. This D of Q is assigning to D of 0. Q1 D of 0. D of 1. Q2 D of 2. Q3 D of 3, like that. Clear? Next, test bench. Go through the test bench. Run. Waveform. See here. Q1, Q2, Q3, Q4, shifting the data. And here 15 is there. That means take into the binary value. Okay. Now we got the see here. Observe properly. What is the circuit diagram? Serial input, parallel output. Serial input will be shifted one by one. serial input will be shifted one by one. Output will get parallelly at one clock cycle. Okay. So if you see here, input initially 0. Input initially 0 here. Clear is high. Whenever clear is high, till here we don't get the output. Whenever clear is high, from here we'll get the output. Okay. So this D input 0, that will be shifted to Q1 here. So Q1 will be getting 0 and Q2 serial shift 0 and Q3 serial shift 0 and Q4 serial shift 0. Immediately we are getting the 0 value at the output, D0 3 down to 0. Until then x and here also x, we didn't got the output. Okay, and then D in is a 1. Whenever D in is 1, Q1 is 1, and then serial shifting 1, and then serial shifting 1, and then serial shifting 1. Immediately whenever all 4 flip-flop got 1, immediately in the same clock cycle only reflecting here. See, that's what we call as a parallel output. But if you take serial, again it will take another clock cycle, and that too we don't get 4 outputs at a time. Again 4 clock cycles to get 4 output. But here in single clock cycle only we got 4 output values. Okay. Clear everyone? Practice, you need to practice. We'll stop here. Okay, because you also have the pending works, right? I will share these 3 codes, whatever discussed today. Try to practice. Parallel in, parallel out, parallel in, serial out, we will discuss in the next session with the bidirectional and universal shift register. Okay, so that registers will be completed in next 1 or 2 sessions. And then counters. Counters also hardly 2 to 3 sessions. One session we will discuss theory part. Next to 2 sessions we will discuss coding. Okay, counters we need to discuss more into some practical examples, like how to write logical things. We will discuss those. Okay, clear? Any doubts for today's session?
No, ma'am.
What about Sunny, Sai, Vinita, Lahari?
As
Clear.
of now, no,
No
ma'am.
doubts, ma'am.
Okay, so practice, do
Yes.
practice. Okay, assignments also don't skip. Those are very important to get practical knowledge. Okay. Okay, then thank you all.
Thank you.